Welcome back, and in this video of part 3 we will continue with another example which follows the previous example 1 we did in part 2. Okay, for this example we are asked to calculate the internal forces at the midspan of beam B2, which has a length of 4.5 meters. We have a point load from beam B1, which is at point A, which is about 600 millimeters from the end of beam B2 at point C. The factored point load was worked out to be 27.265 kilonewton. We will ignore the self-weight of the beam and any other minor loads for the sake of simplicity of completing this example. Right, okay, let's get straight into it. And first we need to work out the reactions at point C and point D. Like we did in part 1, we'll take sum of moments at C is equal to 0, therefore minus 27.265 times the lever arm of 0.6, minus because it's clockwise, plus FYD multiplied by 4.5, and that is plus because it's going anti-clockwise around C. Therefore FYD is 3.64 kilonewton, and again the answer turned out positive, which means the direction of FYD we have assumed up is correct. Sum of forces in the Y is equal to 0, FYC minus 27.265, which is going down, that's why it's minus, plus 3.64 is equal to 0, FYC is 23.63, and that is positive, again that's going up. Sum of forces in the X is equal to 0, therefore FXC is 0, there are no horizontal forces. Okay, now it's time to draw the lovely shear force and bending moment diagrams. Let's start with the shear force first, and we usually start from left to right. So we are going up 23.63 kilonewton, then go right until you meet the point load, then we go down a magnitude of 27.265, which leaves us with about 3.64 kilonewton, just below the beam. Then we keep going right until we are at the roller support and finish up at 3.64 kilonewton. Now I hope so far this is straightforward and easy. Then the bending moment diagram is simply the antiderivatives of the shear force diagram. The slope of the moment diagram is basically the area of the shear force diagram. So from the left side we can say the area is 23.63 multiplied by 0.6, which is 14.2 kilonewton meters. Or if you want to take it from the right side, it's the same thing, it would give us the same results. So that means it will be 3.64 times the length of 3.9, and it's 14.2 kilonewton meters. Right, now it's time to do a cut and take a free body diagram around the area that we want to determine the internal forces. In this case it's at 2.25 meters from support C, halfway. Okay, if we look at the left side of the cut and assume an internal positive sign convention, we will see shear force down, bending moment anti-clockwise, and normal force tension outwards. Okay, now let's determine these internal forces, VI and I and MI. Take sum of moment at the cut equal to 0, and that will be minus 23.63 multiplied by 2.25, again minus because it's clockwise, plus 27.265 times the lever arm of 1.65, and that's anti-clockwise, plus MI, which we have assumed to be positive anti-clockwise, and therefore MI, the internal moment, is 8.2 kilonewton meters. Sum of forces in the Y equal to 0, that's 23.63 minus 27.265 minus Vi, which we have assumed downwards, okay, positive downwards, and that will be 3.64 kilonewton. And that is no surprise because we did it in the bending moment and shear force diagram. Sum of forces in the X is equal to 0, and therefore Ni is equal to 0. Then let's look at the final bending moment and shear force diagram again with all the results of the internal forces. And here we can clearly see the internal shear force is the same right through the beam after the point load. So we could have easily found out that the internal shear force Vi being 3.64 just by looking at the shear force diagram. And that's exactly what I've been talking about. It's so important to draw these diagrams so that we would know what's happening internally throughout the length of the beam. And also from the internal bending moment, because we have a linear diagram, we could have worked it out using the similarities of triangles, and that would have been a lot easier than taking a free body diagram, but I thought I'll do it that way so I can show you both methods. So let's say we have the unknown Mi at 2.25 meters. So we can then say Mi divided by 14.2 is equal to 2.25 divided by 3.9. And guess what? Mi yielded exactly the same results, which is equal to 8.2 kilonewton meters. And from there you can work out the bending stresses and shear stresses and work out the section capacity of your beam. Yeah, so we hope you've enjoyed this video and found these examples were easy and straightforward. If you found it helpful, please subscribe and share so others may benefit as well. I want to thank you for watching and have a great afternoon.